Alright, describe and label each point. We want to tell if these are relative maxes or mins, absolute maxes or mins, or neither. So if we look at this, what would be your absolute max? Well, if you look at it, your absolute max is the highest point, which is E. So with absolute max and mins, you can include the endpoints. So E is going to be your absolute max. Now, C would be your absolute min, but it doesn't exist. So there is no absolute min, actually. C would be an absolute min, but it's not, because there aren't any, because it doesn't exist. You can't just go and say, oh, now I think it's D or A. You can't just go, because isn't there a number right above C on both sides that could be it? So you just basically see there's no absolute min. So relative, well, B is a relative max. C is actually a relative min. It is a valley. Okay, but the problem is it doesn't exist. So if it doesn't exist, can it actually be a relative min? It would actually have to exist to be a relative min, but if that was full, could that be a relative min? Yes. So C is actually neither. Okay, D is neither. We have a lot of neithers on this one, because D isn't a height or a top. It's not a relative. It's not a hill or valley. It's nothing. So D is dumb. A could have been a max or min, but is there something higher? Yeah, this one's higher and this one's lower, so A is neither as well. Again, this kind of messed it all up. There would have been an absolute min here. This could also be called a relative min. All right, number 18. If we want to find the critical numbers on this interval, what we got to do is find the derivatives and set them equal to 0. So our derivative, 2 secant, derivative is secant x tangent x. And then plus, what's the derivative of tangent? Well, that's secant squared x. There's our derivative. What we now do is set our derivative equal to 0. So when I set it equal to 0, I'm going to pull out a secant, leaving you with 2 tangent x plus secant x. From there, well, you set each of these equal to 0. 0 equals secant x. And you got 0 equals 2 tangent x plus secant x. This one could be a little complicated. Hopefully this one's pretty simple. 1 over cosine x. And for critical numbers, do we set top and bottom equal to 0? So for critical numbers, we're basically going to set when does cosine x equal 0? And if you think about the unit circle, where does it equal 0? Well, it would be at, where's cosine 0 would be pi over 2, 3 pi over 2, dot, dot, dot. Are both of these in the interval? If we go farther, we'll be getting out of the interval. So these are the two we got. So these two are actually critical numbers. You could keep going, but those are the two in the interval. Now, to solve this one's a little bit harder. Here's what we're going to do. 0 equals 2 sine x over cosine x plus 1 over cosine x. And if you look at that, it's kind of interesting. That becomes 0 equals 2 sine x plus 1 over cosine x. Okay? Do I need to set the bottom equal to 0? No, I did it already. So I don't need to go cosine again. But if I set the top equal to 0, well, you can solve this. If you minus the 1 over, and then divide by 2, oops, divide by 2, you got sine x equals negative 1/2. So when does sine of x, when does the height give you negative 1/2? So what values would that be? or the height is negative 1/2. That would be on the bottom of the unit circle at both, oh boy, I should have thought of these. Is it 5 pi over 6?
7 pi over 6.
7, thank you. 7 pi over 6 and 11 pi over 6 are the two where sine is equal to negative 1/2. So those would be your other critical numbers. So these are critical numbers. These are possible hills and valleys, okay, or other critical information about these, or important values we'll talk about more as we go on.